Okay, welcome to note set 28, where we'll talk about application of eigenvectors, eigenvalues, eigenvectors, eigenstructure. And what we're going to look at is how to maximize a quadratic form. And actually, this is should really be called constrained maximization of a quadratic form, as we'll see in just a minute. So the reason I'm presenting this is that I've been harping on this idea that eigenvectors are everywhere in electrical and computer engineering. And I think in the last video I was even apologizing, saying, gee, I keep saying this is everywhere, this is everywhere. And I feel bad that I can't really show you everywhere that it shows up. But as I said in the last video, I can't really take the time to do that because you just don't have the background yet to be able to see where all these things show up. As you get into your junior year classes and especially into your senior year classes, even then you'll start just only barely seeing where these kinds of things show up. They may play a secondary role in the way it's presented at the junior level. Senior level, there we go again. At the senior level, you may see a little bit more insight into this, and certainly when you get into the graduate level is when you really start seeing these things being applied to ECE problems. Now you might be saying, geez, I gotta wait till I become a graduate student? I don't even want to be a graduate student. Well, just let me give you a little heads up here. These days, the engineers that are doing the most creative work in companies have at least a master's degree. It didn't used to be that way, but these days it's almost becoming to the point where if you're going to be a person doing real electrical engineering design work and development work, a master's degree is probably almost a requirement. All right, anyway, this set of notes will give you some insight into how some of these eigenvalue, eigenvector, eigenstructure problems show up in at least an electrical engineering problem, but there are similar things for computer engineering. And the areas in electrical engineering that these things show up, I know less about computer engineering because that's not my background. But antenna design, where we're using multiple antennas to enhance our ability to receive signals. So I mentioned that last time, that in the base station, when you've got these multiple antennas there, they may be using this eigenstructure mathematics to figure out proper antenna design, as well as algorithms to process the signal once they've been received. And so that carries over into wireless communications in general, and then things like radar and sonar for various mainly for military applications, although clearly both of those are used in commercial airplanes and boats, obviously. But the cutting-edge technology is developed in the military setting for those. Seismic sensing, so we might be trying to explore underneath the earth to determine what's going on, either naturally occurring signals under the ground, vibrations and such, or in the concept of geophysics, where we might be actually sending signals down into the earth, having them bounce off the structure underneath, and then we process the reflections to try to figure out, where's the water, where's the oil, where's the natural gas, and so forth. Control systems, so navigation systems that keep you on a certain track, or control systems that, like a self-driving car might have, or autopilot in an airplane, things like that. So all of these areas end up with these quadratic forms showing up naturally, and largely it shows up from the energy point of view, and we'll see how that comes in to play here in just a little bit. So before we can get into this particular application, I'm going to cover a little bit of general linear algebra stuff that we have not yet covered. Some of it we have, and I'm just going to reiterate it or maybe recast it here. So let's start off with an n by n. So I'm using capital N here. The book has been pretty systematically using little n here. Doesn't really matter. We're going to do an n by n positive definite matrix R. What we want to do is find the unit norm vector that maximizes. We're going to focus on the maximizes, but we could also be looking for one that minimizes, depending on what we're trying to do, this quadratic form. So for convenience, we'll just use this notation. We'll call this, it's a function of the vector x. So for every vector that we plug in here, we'll get a number that is the value of that function. So you're used to seeing a function versus a scalar variable. So whatever that is, might look like that. That could be just some arbitrary function. But there's no reason why we can't imagine having another axis and we have some sort of surface. I can't really draw that. We'll see a picture of such a surface in just a little bit. Now you've got some sort of sheet, some bending sheet that's above this two-dimensional plane. So we might have x1 on this axis and x2 on this axis. We could extend that to however many elements we have in our vector. So our notation for this maximization problem looks like this. Now you've probably seen something like this notation in your calculus class or other math classes. So here's the thing that we're trying to maximize, our quadratic form. And so let me tell you a little bit about what this argmax means. So if I didn't have the arg there, let's ignore that for the time being. What I'm trying to do here is I'm trying to maximize this value over all possible values that it can take, with the constraint that the norm of x must be equal to 0. So if we're stuck in this two-dimensional space, x1 and x2, where our vector x is now two-dimensional, we're basically limiting ourselves to living on a circle of radius 1. That's what this constraint does. So we're basically saying walk around this circle, look at the value of this function at every point on that circle. So that would be along an axis that would be sticking up out of the plane, out of the screen here. And so since we know that this is positive definite, we know it's going to be above the 0 point. So it'll be above this x1, x2 plane. So we can imagine walking around this circle and looking above us and saying, at what point on the circle is that function the highest above me? That's the maximization. So we're maximizing this. Let me clear some of this ink off. We've gotten terribly clouded here. We're trying to maximize this over a set of x that's constrained that way. And if we didn't have the arg there, the value that I would be returning would be the actual maximum value of that. That's what max is. But with the argmax there, I'm still trying to find I'm still trying to find the maximum of this, but what I'm returning is the value of x that meets this condition while still maximizing this, and it's that x value that gets returned here. That's what the arg tells us. You can think of arg as shorthand for argument of the maximum. So argument we use in math to mean the thing inside a function, and we use it for a variety of other things. So argmax means to find the maximizing value of x. But we have a constraint. So this is a constrained maximization problem. So we're trying to maximize a quadratic form. What does this thing look like? Well, we've seen this a little bit already. We've seen that quadratic forms give rise to ellipses and things like that. Well, let's look at the two-dimensional case. So we've already talked about this in the last set of notes. So we've got x transpose, which is 1 by 2. R, which is 2 by 2 in this n equal to 2 case. We've got x, which is 2 by 1. So when you do all that multiplication, these things match, and we're left with a 1 by 1. So the result is a scalar value. So this is a function of two variables that gives me one number back for each of those. So you plug in some number for x1, some number for x2, and you get a functional value. And we've already seen how we can expand this out and we get something that looks like this. And remember, since we're talking about a positive definite matrix R, it's symmetric, so those R12 and R21 are the same. And in the previous set of notes, if you remember, we left off this and we wrote a 2 here. And we also talked about, since these are quadratic terms, and these are kind of biquadratic term, we call this a quadratic form. And when R is positive definite, and we set this equal to C, what we're trying to do is find the set of all x's such that this function here takes on the value of some number C. And I don't state it here, but clearly that needs to be greater than 0. And we've seen how that defines an ellipse. And so all that we're doing is we're looking at this function here and we're imagining slicing it at different heights and seeing what the outline of that slice looks like. So here's the quadratic surface. So let me clear off some of the ink here so we can see a little bit better. So if we were to plot this function as a function of x1 and x2, I don't show the axes here, but we've got a set of axes here, x1 and x2. I've drawn them, they don't really look orthogonal, but I've drawn them so that you're kind of looking at them askew. So over those x1, x2 axes, here's what that function looks like. So at this point, I go up, and that's the value. Now, if I walk around in a circle, scratch that, walking around in a circle bit. If I slice through at a given height, imagine taking a, sorry for the phone, we'll let that ring through, and should do 2 rings, and then the answering machine should get it. All right, good. If we slice through that we're getting these ellipses. And we can see that as we raise the height of where we slice, the ellipse should get bigger and bigger and bigger. The height of the cutting is what we set by C. So that's what we're doing when we set this quadratic form equal to a specific number. We're saying, give me the values around this at a specific height. And that's what these different ellipses show. So what we want to do is, given this quadratic form defined by a positive definite matrix R, we want to solve this constrained maximization problem. So why should we have a constraint of x norm equal to 1? Well, if we don't constrain it, what would be the maximum of this? Well, let's go back and look at our picture over here, back here. If I just keep going further and further out this way, this thing just keeps growing bigger and bigger and bigger up, right? It looks sort of like, let me just go back over here, if we were to look at a one-dimensional version of this. So here's x, and looking at this quadratic form of that, maximize that quadratic form, no constraint, right? This just keeps going up and up and up. So the max will occur, will keep getting, or the height of it will keep getting bigger as I let x get bigger and bigger and bigger. Well, what if I want to limit how big x can be? Well, then the max will occur, in this case, right there, over that limit. So that's similar to what we're doing here, except in the 1D case, limiting x to have magnitude of 1 really is easy to figure out where it is. There's only two possibilities of x that will be have magnitude equal to 1. But for this problem, in the two-dimensional case, it's quite a bit more interesting. And as we go to higher dimensions, it gets even more interesting. So all we're saying here is that we can make this thing as big as we want by just picking bigger and bigger x's. So we have to put a constraint on this. Otherwise, there's no real solution to this. I mean, the solution is just x is infinitely large, and that's not good. The other reason, a more physical reason, is that x often accounts for some physical thing that we're trying to create, and we may have some constraint on how big that physical thing can be. So when we get into the application here, I'll comment on that to some degree. But from a more mathematical point, this constraint puts the focus on the effect of r, not just making x bigger and bigger and bigger. So technically, we could constrain this to be equal to any number k, but we'll see that without a loss of generality. And sometimes if you go into more mathematical work, you'll see this abbreviated WLOG. So it looks like maybe something someone might text you, WLOG, without laughing overly gregariously. I don't know what that would really mean in text. Maybe there is a WLOG and you know it because you text, and I really don't text that much, just with my family. And yes, I'm old enough that I usually spell everything out in my texts. I know that's sad. Anyway, without loss of generality, we can choose k equal to 1, norm is equal to 1, norm is equal to 1 for our constraint. So what are we trying to do? So here's our picture, and let's add this constraint. So in this two-dimensional case, I've already said that the vectors x that have a norm equal to 1 will lie on a circle, right? Because that's their length, right? So every vector that lies, whose tip is on this circle, has length equal to 1. And like I said, we could make this circle bigger, and we'll see later that or we can make it smaller. We can make it be equal to some k, which is greater than 0, and it will work just the same. So what we're trying to do here is find the x that lies on this circle, that's the constraint here, that maximizes this. And so these contours are remember, slices of that actual quadratic function. So remember, on this ellipse, the values of the function are bigger than the values of the function on this ellipse. Now you might say, why are there these specific ellipses? In reality, there's infinitely many of them. I'm just slicing at a few select heights, right? So if we go back here and we look at this, no matter where I slice, I'm going to get an ellipse. And if I slice, infinitesimally higher and higher and higher, well, I just get the sequence of this function. But if I say, well, just for graphical illustration purposes, I'm going to, slice at evenly spaced heights, I'll get a bunch of contours that look like this. So those are probably created, well, I drew those with PowerPoint. But I was aiming at saying those are, for some maybe uniformly spaced heights, something like that. I don't know for sure. Like I said, I just drew it with PowerPoint. Okay, so back over here. So here is our unit circle. In higher dimensions, we would call it a unit sphere in higher dimensions. And so we want to look at all the x's on that red circle and find the ones that will give us the largest value of the quadratic form. And so we can pretty much see that where this circle just touches an ellipse will give us the solution, right? So clearly if we were over here, we're on an ellipse that's inside, and since this thing curves up like that, our quadratic form curve, I'm horrible at drawing, since this thing curves up on the sides like this, moving outward like this goes to higher values of the function. So clearly, if we look at operating at this point, we have a larger value of our quadratic function than operating here. And obviously this would be the point that would minimize our quadratic function, but we're maximizing, not minimizing. So think about these curves here as the lines on a topographical map. If you've ever looked at one of those, you can see which direction you should go to stay level. So if I'm here and I wanted to walk in a direction that would be neither uphill nor downhill, I would need to walk along this curve. But if I were to walk from here to here, I'd be going downhill. So think about it that way. So we now know where our solutions need to be. So the solutions are the unit vectors that lie on the ellipse's minor semi-axes, right? Here's the major semi-axis here, and here's the minor semi-axis. So in the previous set of notes, I called these the principal axes. And remember I said there's another name for them that I couldn't remember at the time. They are called the semi-axes. So the minor semi-axis is the one across the shorter side, or the shorter distance across the ellipse. The major semi-axis is the longer one. Now you might say, well, hey, a circle is an ellipse. Which is the minor and which is the major? Well, you can't tell on a circle, right? Okay, so that's what we're trying to do, and we note that, we know that the vectors lie on the ellipse's minor semi-axis. We also already saw that the tilts and structure of an ellipse, its orientation is set by what? The eigenvectors. And we also saw that the distances along those eigenvectors, we saw that the eigenvectors go like this and like this. And the lengths of those were set by the eigenvalues. And remember, this length was set by the larger eigenvalue, and this was set by the smaller eigenvalue. So keep all that in mind as we go through this. So how do we mathematically solve this maximization problem? When we're solving one in higher dimensions, which we'll be doing very soon, we can't really just draw the picture and figure out where it is. We need to have some sort of mathematical result that tells us how to do it in these higher dimensions. So when we maximize something in your Calc 1 class, how did you maximize something? Well, you differentiated it and set the derivative equal to 0. Now, there were some conditions in order to assure that actually gave you a maximum. And sometimes differentiating and setting to 0 does not give you the maximum, but that's the approach that we generally use. But unfortunately, we can't do that. And the reason is that we're not really just maximizing something. We're doing a constrained maximization. So we can't just differentiate our quadratic form and set it equal to 0. In fact, if you look at this, I know you have not had Calc 3 yet, where you would have talked about this, but let's look at our our one-dimensional quadratic form. Clearly, the derivative of this thing will be whatever the tangent is. Where is it equal to 0? It's equal to 0 right there. There's our derivative that's equal to 0. That will only find the minimum of this. It will not find a maximum, and it certainly will not find a maximum if we put some sort of constraint on it, that we can only consider this point or that point, or maybe just points in between those. Can't do it. Will not work that way. So differentiating will not give us the answer. So this is what's called a constrained maximization, and we need a little more mathematical heft to do that. And there is a method, maybe you may have heard about it, maybe not, doesn't matter, called Lagrange multiplier. And again, I'm doing this to show you where things are coming from. I know that students often think about, like, what's going to be on the test? What's going to be on the test? This is not going to be on the test. So sit back, relax, absorb it, become a good engineer. Don't worry about the test. The real test will be when you get out into the real world and you become an engineer. So absorb this stuff now. Learn it, absorb it, integrate it into your thinking. Do you need to remember everything about it? No, but you should be remembering the big ideas. Oh, yes, there was this thing called Lagrange multiplier. What was it for? Constrained maximization, or equivalently constrained minimization. Yeah, I need to go look at that. Sometime in the future, you'll say that. Okay, so for right now, we're not going to worry about where this comes from, but there is a pretty easy way to prove that this actually works, and it pretty much involves linear algebra coupled with Calc 3. So we're not really going to go into the details of it here, but it's a fascinating idea. Anyway, Lagrange, well, you've heard of, other French mathematicians, perhaps. Lagrange was a French mathematician. I always like to joke that a lot of electrical engineering is based upon the results from a bunch of dead French mathematicians. We've got Fourier, we've got Laplace, we've got Lagrange, and there's other dead mathematicians of other backgrounds, not just French. But a lot of electrical and computer engineering is based upon results of now dead mathematicians, because they developed these results long ago. Anyway, Lagrange figured out a way to do constrained maximization. And what Lagrange said was, let's create a new function. So we did have our q sub r of x. We're going to create a new function that we'll call j. That's a function of the same thing. And here's the thing that we're really trying to maximize. That's our q sub r of x. That's our quadratic form. So you put the thing that you want to really maximize there, and then you put some variable, and we'll use lambda here for a couple reasons. One, lambda sounds like Lagrange, so a lot of Lagrange results use a lambda there. So it's kind of a historical letter to put there. But also, we'll see that this ends up being an eigenvalue, or it ends up playing the role of an eigenvalue. And so for this problem, and so we've used lambda for eigenvalues, so that makes sense. So we just put a variable out here, and it multiplies this thing, and so that's why it's called the Lagrange multiplier. And what does Lagrange tell us that we should multiply by the multiplier? Some function that captures the constraint that goes to 0 when the constraint is equal to 0, or when the constraint is met. So basically this is a linearity constraint, and so what we do is we put the thing that we want, that's there, and minus the thing that we need it to be equal to. So that's how we set that up. And so now Lagrange says this is a new problem to solve. And here's the remarkable thing. It transforms a constrained maximization into an unconstrained maximization with an extra step. So we're going to do two steps to solve this. The first one is solve this, maximize j of x with respect to x with no constraint. I really should have written that right here, with no constraint. Maybe I'll remember to go and modify the notes before I convert them to PDFs. So solve this as an unconstrained problem. So that means we can apply differentiation and setting to 0 for that. And when we solve that problem, we will find the solution, but the answer will still depend upon the Lagrange multiplier variable lambda. We don't know what lambda is. The trick will be to solve this first problem and then pick the value of lambda to meet the constraint. And so that's the second step. We then massage that solution, it being this answer. We massage it to impose the constraint. And that will lead to setting a specific value of lambda. So in other words, we end up with a whole family of solutions to the unconstrained maximization problem, where there will be for each lambda a specific solution. Then we just adjust the lambda so that the solution matches our constraint, and that will be our answer. So let's do this for this problem. We're going to maximize this cost function here, the Lagrange function, j of x, just the standard way. Now, I know that you've not had Calc 3 yet, but it's just a pretty straightforward extension of the idea of taking derivatives of things, except now we're taking derivatives with respect to more than one variable. So we don't just have an x as a single variable, we've got an x1, an x2, an x3, all the way out to xn. So we have to differentiate this that way, using this extension of differentiation. We set that derivative equal to 0 and see what we get for our solution. So like I said, this uses some results from Calc 3, but they are similar to Calc 1 results, and the results that we need to use are called partial derivatives. So they work just like regular derivatives, but the idea is that we just take derivatives with respect to one variable while holding all the others fixed. Now the other thing here is that we're taking a partial derivative with respect to a vector full of variables. So that's another Calc 3 result. And we're going to just kind of wave our hands over that. And so when you get to Calc 3, you'll learn how to do these things, but the result will look like this. So let's just take a minute and just, even though we don't know anything about partial derivatives and we don't know about derivatives with respect to vectors, we can kind of make sense of this. Remember, this is a quadratic form, so this is sort of like a times x squared. And when you take the derivative of that with respect to x, what do we do? Derivative of that with respect to x, what do we get? So this is a d here, not a 4. We get 2 times a x, right? That's one of the simplest derivatives that you'll ever see, right? So these things here are funky d's, little funky d's. They are called differentials, just like we have in Calc 1, but these represent partial derivatives. But what are we doing? We're differentiating something that's sort of like a quadratic, right? It's sort of like an ax squared. R is playing the role of the scalar a, and x transpose x, even though they're on each side of r because they need to be, are kind of playing the role of an x squared. We saw that when we expand this out, we get a lot of x1 squareds, x2 squareds, and so forth. And if you work all that out, you get that this term, this derivative, becomes this. And look, it looks an awful lot like that. Remember, r is playing the role of the little a. We get a 2 out in front because of the square being differentiated. And we're left with an x. We're left with an x. Now, you might be wondering, what's with the hat? Well, it's cold outside. Actually, it's not. It's like 90 degrees right now while I'm recording this video. I'll tell you about the hat in just a minute. Let's take the derivative of this term. So this is, again, just like taking the derivative of a quadratic term, except it's just 1 times x squared is the analog of this. And we have a lambda out in front, so you can pull that out. So again, we get 2 times x, and again, we'll put a hat on it. And this negative sign carries over to the negative there. What about this last term here? That's this lambda times 1. We're going to take the partial derivative of that with respect to x. Well, as far as x is concerned, lambda does not depend on x. It's a separate variable that when we're differentiating with respect to x, we treat as a constant. So the derivative of a constant is 0. And so there is no term in here. There's nothing in there for that. Okay? And then equal to 0. So equal to 0. We're setting the derivative equal to 0. Okay, so why the hat? Well, I use the hat to indicate the value of x that satisfies this equation. So x hat is representing not just any old x, right? Up here we're writing this as any old x. Now that I've differentiated it and set it equal to 0, the one that satisfies this equation is the answer. So I have to call that something different. It is x hat, a special selection of x. And so now I just need to rearrange this, and I can pull this over here. Now, technically, my R is a square positive definite matrix, so I know that it's invertible. So I could solve this. I could find R inverse and put it over on the other side, but that doesn't help me because I've got an x hat on each side. How do I solve this? Well, we've done this. This is the eigenvector problem, right? So what we're saying is that the x hat that solves this, which maximizes this unconstrained problem, is an eigenvector of the matrix R. Ha! Who would have thought that would have showed up? But it does. Yet another connection between eigenvectors and quadratic forms with positive definite matrices in them. So the maximizing vector x hat is an eigenvector. But remember, this lambda is just showing up. We don't know what that is. We don't know what value of lambda we should pick. So it's an eigenvector, but which one? Which of the eigenvectors is it? And so that's where we see that our answer at this point, after the first step, still depends on the variable lambda. So let's go back and look at our steps here, right? So, at the end of step 1, we get an answer that will depend upon the variable lambda. We don't know what lambda to plug in yet. Second step is figure out the lambda to pick that will make the solution satisfy the constraint. So that's where we're at. So we move on to step number 2. Step number 2 is make result of, this should be step number 1, meet the constraint. I'll try to remember to fix that in the notes that I post. So let's plug our solution into the problem. We plug x hat into our quadratic form. So we don't yet know which x hat it is, but we do know that whichever eigenvector it is will have its corresponding eigenvalue. So, and this is because x hat is an eigenvector. I'll fix that also. Eigenvector. Okay, so with a corresponding eigenvalue lambda. So now we rewrite that like this. But what do we know? What do we know about our constraint? Our constraint has to be such that the norm of our solution, our x hat, has to have unit norm. Well, there's the norm of it. Well, norm squared, sitting right there. Norm squared, well, if the norm is equal to 1, the norm squared must be equal to 1. So we enforce the constraint that we're only searching over x such that the norm is equal to 1. So x hat, in order to be a solution, must have norm of equal to 1. So now we have that at our solution, the actual value of our quadratic form is equal to the corresponding eigenvalue. So for the two-dimensional case, we've got two eigenvectors, each of which could properly solve for step number 1. So if we put in if we put in one of them, we'll get its eigenvalue here. We put in the other one, we'll get its eigenvalue here. So which one should we put in? Well, we're trying to maximize this, so put in the eigenvector that has the largest eigenvalue. So, aha! The maximizing vector x hat is the eigenvector with the largest eigenvalue. And since we can always normalize any eigenvector to any length, we will normalize that to unit norm. But the important thing is we have to pick the one that has the largest eigenvalue. And this is a classic result that shows up all over the place in electrical engineering, computer engineering, all sorts of engineerings, all sorts of sciences, computer science, physics, everything, all over the place. Very, very classic result. To maximize a quadratic form, we pick the eigenvector with the largest eigenvalue. And so here's our picture again. Here's our quadratic surface. Here's our circle. We are limited to picking an x on this circle. We want to pick either this point or this point. It doesn't matter which one. Both of those are eigenvectors, right? We want to pick it to have unit length. That's that. So it'll lie on that circle. And we note here that the solutions lie on the minor semi-axis of the ellipse. And remember, we already established in the last set of notes that the eigenvector along the narrow part of the ellipse has the larger eigenvalue, because this length here, the length of the eigenvector, when set equal to a certain k value, was related to 1 over the square root of the eigenvalue. So picking the largest one makes that the smallest distance. So the maximum eigenvector lies along, the maximum eigenvalues eigenvector lies along the minor semi-axis. So we've solved the problem. We figured that out just by looking at the 2D picture, but we didn't make the connection to the eigenvectors necessarily. So now we know how to maximize a quadratic form. How do we minimize? Again, this is constrained. So let's go back over here. Obviously, unconstrained minimization would always be at 0, 0. So we still need a constraint. We can't let this go to 0. So we put the same constraint, minimizing along this circle. Where do we want to be? Well, this was maximizing because we hit the farthest out ellipse that touches the circle. Well, we've already said that this will give us the smallest value of this. So minimizing, we could go through the same Lagrange multiplier problem, but we know the answer already from having gone through it once. We know that those are our solutions. So the solutions are the unit vectors that lie on the ellipse's major semi-axis. So the minimum eigenvalue eigenvector lies along the major semi-axis. All right, so that's all just setting up some mathematics that we're going to use. And now we're going to apply this to something that I'm going to call acoustic focusing. So, long time ago, when I was a graduate student, I was walking in Watkins Glen Gorge. If you've never been up there, you ought to take a trip up. It's spectacular. But there was a circular wall that, if you stood in just the right place, when you spoke, it sounded like you were speaking inside your head. The physics of that wall were such that when you stood at exactly that right place, all the acoustic energy of your speech ended up being focused right back to your ears in such a perfect way that it sounded like you were speaking from inside your head. It was really quite a weird sensation. And I just happened to walk through that spot while I was talking, and then I had to go back and, kind of move around a little bit to try to find that spot, which made people around me look at me rather strange, and made my girlfriend at the time maybe want to walk away from me because she didn't find it that funny. Anyway, that's the price you pay for dating an engineer. But we're going to look at a similar problem. Can we make that kind of thing happen? Now, I will say that this, as I'm setting it up here to just try to make it easy to set things up and illustrate something, I've created somewhat of a contrived scenario. I can't think of any real-world application where you would really do it exactly like this, but it's so close to other things that you really would do that it at least conveys the essence of it. And it at least should get you thinking about some of these ideas and realizing that, wow, these things do show up in real-world engineering problems. Now, the other thing that I want you to see from this is to just see how engineers think through the application of mathematics to some real problem. That's how real engineering is done. Some engineering is just done where you say, gee, I'd like to make a gizmo that does this, and oh, look, I can buy this part and this part and this part, and if I connect them together, it does this. Okay, yeah, that's kind of engineering, but it's more tinkering. Real engineering solutions come from saying, well, I have no clue what to make this happen, or how to use the components that I might have available to me to make something happen. How do I figure that out? The way we do that is we model things with mathematics so that we can work out what the right solution is. Then we figure out how to make it happen with what we have available. So that's what we're going to look at here. So suppose we've got some sort of waveform generator. So that just makes some sort of sound. It can make any kind of sound that we want, any kind of sound waveform. And we've got an amplifier to boost that up to more power, and we run it through a speaker. So this is like, what you may have as your stereo system in your home or your apartment or your dorm room. I don't know that people have stereo systems anymore, but it's something you might plug your iPod into so that you can hear it during a party. And the waveform generator we can think of as nothing more than perhaps an iPod with some pre-recorded signal on it that would just continue replaying over and over and over. And so out of the speaker comes some waveforms, and I'm showing those things like the ripples in a pond when you drop a stone into it. So those are the wave fronts of the acoustic waves that are emanating from that speaker. And then we've got a bunch of reflectors out here. Those could be, walls or columns or mountains or whatever, furniture. And I'm just showing those as nice little circles, maybe spheres or something like that. Don't worry about what they are, but they're going to reflect the waveforms. So if there were no reflectors there, these waves would just continue straight through. And we'll still get those waveforms that continue straight through. The effect of the reflectors is that the waveform will come out of here hit here, and then bounce over there. It'll come out of here, hit there, and then bounce and go to the target. So these wavefronts here are coming from a reflection from this reflector. So this is a very common way of modeling wave propagation, whether it be acoustic waves or electromagnetic waves that we use to send, radio signals for cell phones or radars or things like that. And there's no importance here as to whether it's acoustic or electromagnetic. But I kept it acoustic because it removes some issues of representing how things really work. Now, our goal is to try to get as much acoustic energy or equivalently acoustical power focused at whatever our target is. So this isn't quite my Watkins-Glen problem, but it's almost. Instead of me speaking and having it show up back in my head, it's somebody else speaking and they want to get it directly into me with as much volume as they possibly can. So what's happening here? The target will receive the direct path, that's these red things coming directly from here to the target, and it will also receive a bunch of reflections. I'm only showing 2, but with 5 reflectors, we would get at least 5 reflections. What I'm ignoring here are double reflections. So I'm ignoring, something that goes here and then bounces to here and then goes to there. And I'm also ignoring, triple and quadruple. The reason that we can often ignore those is that because they've been reflected multiple times, they become very weak. Each reflector will lose some amount of the sound energy. And so we can approximate this and say, ignoring those. That's another thing that engineers do when we think through the application of math to a real problem. We often try to say, well, I could model everything, but then I certainly could do that, but the model then becomes so complicated that I can't solve the problem. So having a perfect, super complicated model doesn't actually help me all that much. Obviously, as we progress in our understanding and ability to solve these things, we do strive for more and more accurate and complicated models. But when we're first starting out, we often do some serious simplifications just to get a handle on the problem. So we're going to just assume that each reflector has something bounce off from it and go towards the target, and that anything that bounces from a reflector to another reflector to the target can be ignored. So we've got a bunch of different wavefronts all converging here on the target. And so, as you learned in your physics class, there are constructive and deconstructive interference happening at the target. And so what we want to do is try to control that so that we can maximize the constructive interference and kind of minimize the amount of deconstructive interference that happens. That way we'll get the maximum amount of signal volume at our target. So if there were no reflectors, so now we're going to try, once we've set the problem up, we're going to try to model this mathematically, and you'll be amazed at how we end up with a quadratic form problem that needs to be maximized. So if there were no reflectors, our signal, which we can just think of as a function of time. So as time goes on, if you were to look at a plot of music, it would be some wiggling waveform. So as time goes on, we've got just a function. This is x of t. We've got a function x of t. So it takes on some value at each instant of time. That's how we model a waveform. So each signal coming from a reflector will take longer to arrive than the one that went directly. So the one that arrives there directly we'll call x of t. But coming from the first reflector would be x with some amount of delay. Now I'm not going to go into the mathematics of why that accounts for a delay, but I think you can kind of see it. It'll shift the function to the right on my time axis. Therefore, it's a signal that's arriving a little bit later. And it will have some coefficient out in front that captures the reduction of energy due to the reflector. And this will account for something coming from the second reflector and the third reflector. So, this last one here will be the reflector whose path is the longest. So if we go back to our picture here, whichever one of these has the shortest path, so that might be this one because it hardly deviates, would certainly be the shortest path, and then which one is the next one, I don't really know for that particular setup. But we can put them in order, and we just put them in order so that we can, kind of index them in order. Okay. So now we're going to use a little trick to approximate this problem. It's along the lines of how you approximate an integral by slicing it up into a bunch of rectangles. But we're not doing the rectangles. We're just doing the points at the edges of the rectangles. So our function y of t, that's the signal received at the target. We can just think about looking at it at points spaced capital T apart. And if we make capital T small enough, this will be a reasonable approximation, or it'll give us enough view of this signal to figure out how this problem behaves. And then we do the same thing everywhere else there's a T. There's a T there, so we put that there. There's a T here, so we put that there, and so on. And then here's the other trick that we're going to do. I have no idea whether this delay here can really be written as some integer multiple times times some capital T, but I'm going to assume that it can be. And by making T, capital T, small enough, I can approximate that. So suppose I say this tau sub m1 maybe is a number that think about a piece of lumber that is as long as that number is. Okay, now capital T is telling me some spacing that I'm slicing this up into. If I make T small enough, I may end up having a little bit hang over at the end. Here's my next spacing of capital T. It's not quite exact, but I can say, you know what, it's close enough. This is engineering. This is how we model things. We approximate, but we do controlled approximations. So once we've done all that, and again, this is not going to be on the test, just sit back and enjoy it, observe, absorb. We can now model this as indexes in vectors. So I switched to the square brackets to illustrate that I'm not talking about this function that's on a continuum anymore. I'm not talking about this function that is on a some sort of continuum function. I'm just talking about a vector, and I'm using the square brackets to call that into focus, to just distinguish it from what I had above. And so now all I'm doing is saying that this vector x indexed at n will give me the value of the original function evaluated at n capital T. Okay, and same for all the rest. Okay, now comes the fun part. So we have this discrete or approximate model. So discrete means not on a continuum. We have discrete indexes here. So it's like we're indexing into vectors like we've been doing all summer long, all semester long, whether you're taking this course in the summer or semester, I don't know. And we can now look at these samples of y of n and see what they are. So at the very first instant, when we very first start to sample this, we get our very first x of 0. And for a while, that's all we see, right? If we go back to this, there will be some amount of time. Let me clear this off. There will be some amount of time where all I'm seeing are the red waves coming in, because the blue waves are taking longer to hit a reflector and get to the target, because it's a little bit longer along this direction than it is along the straight path. So there will be a little bit of time where I'm just getting the direct path signal. And then what happens? Then I start getting, so this is my last instant where I get a sample from just the direct path signal. Then at the next instant, I get the next sample from the direct path signal, but I start getting the first x of 0, but delayed because it was the first little wiggle that bounced off the reflector, took a little bit longer to get there, and gets multiplied by a number to represent that some of the energy was lost in that reflector. And so on and so on and so on. And then I go all the way down, and eventually I add in an additional term. So here's the direct wave, here's from the shortest path reflector, then I start getting the next longest path reflector starting at x0, and so on and so on and so on. So if you're not following this exactly, don't worry about it. There will be future classes that you'll take where you'll learn these ideas, and you'll be armed with more visualizations of this. But so at this point, just if it's not perfectly clear, just accept it. So here's our signal now. We can now model this. And here's the cool thing. Here's where matrices come in. So we can define a matrix H. It's a big frickin' matrix here, because we're imagining sending this signal over a fair amount of time, and we're thinking about taking our samples fairly narrow, fairly closely spaced, so it's going to be a pretty long, pretty big vector. So it'll be clear what we're going to do with this matrix in just a minute, but look at the structure here. We start with a 1 and then all zeros. Then we're going to shift this over by 1 and shift in a 0. So now we have that, and this little 0 got shifted over and fell out of the matrix. You got to have some fun. And we keep doing that. Every time we go down a row, we shift over one more. And so we get this nice little diagonal band of 1s going down. But at some point, when we get a 1 out here, we'll start getting an HM1 here that accounts for the fact that the shortest path reflector starts to show up. Signals coming from that one start to show up. And notice how that goes down diagonally. And then we have the next reflector coefficient going down diagonally. Blah, 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 blah. All the way down to the last reflector going down diagonally. So there's our H matrix. Okay, and each column is shifted. So we've just been explaining this as shifts of rows, but we can also think about it as shifts of columns. So let me back this up just a little bit. You can see that if you look down this column and then you look down this column, you can see that everything is just shifted down. We shift in a 0 and we shift out whatever was here gets shifted out. Oh, all right, good. And we take that all the way over, and we keep shifting down until the last element is this HMP. That's the reflection coefficient for the last reflector, the reflector that has the longest path to the target. So that's the structure. And now I'm showing officially all those diagonal elements there. So we end up with as many columns as there are samples in X of n. So that depends on how long we transmitted. So, if we transmitted for 1 second and we took our capital T spacing, say, every millisecond, then we would have 1,000, well, maybe one more, because it's the fence post problem. But we'd have roughly about 1,000 samples in X of n. And so that would be the number of columns that we have. And we have more rows than we have columns, just because it takes longer for the sound to stop at the target, because some of it is taking longer to get there than the direct path. So the direct path will stop after 1 second. So if I transmit for 1 second, then at the target, if there were only direct path, the sound would start, and 1 second later it would stop. But because of the reflectors, it will stop later. So I'll actually have more rows here than I have columns. And how many rows I have will depend upon how many reflectors I have and how they're actually configured. So for right now, don't worry about how do I know this H. So a lot of times when we're developing ideas for electrical and computer engineering problems, students often get hung up on how do I know what this is? But the seasoned engineer will not let them bother that bother them at first. They'll just go and keep going and say, I'll worry about that later. I just want to see how this works. So that's our structure. So without going into the details of it, but I think you can see that if we imagine taking a vector x that has all of the samples from our received signal x, which would be just with the direct path, if we only had direct path, and so we would have none of these elements down here. If we just multiply our x from the right, the first sample of y would just be the first element of x times 1, and then 0 times all the other. And then the next row would pick out the second element of x. And it wouldn't be down until we get down here that we're picking out, again, the first element of x, which would be x of 1 at this point, and still some later sample from the original direct path. So this actually gives us exactly this structure. So we can puzzle all that out and see how that works. So H, the matrix H, is a model of the reflector's effect. And if you look at this H matrix, I think you can see that, for almost every setup, this thing's going to end up having a bunch of, is going to have all linearly independent columns just because of the way this thing is made. You start with a column and you shift it down, shift it down, shift it down, shift it down. So these things, unless there's, some of these H's are special structures, these little H's, have special relationships. The chance of this thing being non-independent columns is virtually 0. So we've got an H that has independent columns in it. So it's a tall matrix that has full rank. We're getting somewhere. We've talked about these things. And we have this nice mathematical model that says, if I know H for a given reflector setup, and a given transmitter position and a given receiver position, that will specify my H matrix. Now, whatever I transmit, X, will end up being modeled by this, and I can get a nice mathematical characterization of what I would receive. So let's see where we go from that point. So here's what we want to solve. Remember, our problem was to determine what signal should I send to maximize the average power at the target for a fixed transmitted power. That's our problem. So power, remember, is the square of voltage. So we can think about squaring these y values. They're going to be. We can think about putting a microphone at the target and converting the acoustic levels into voltage. So we want to square them, and then that gives us the power of each element. And then to get the maximum average power, we would add them all up and divide by how many we have. So there is our formula for at least something that is proportional to power. And I haven't really said what this capital N is. It's how many samples I have from when I first start receiving a sound at the target to when I stop receiving sound at the target. So my goal is to maximize this, and we can see that this is just the norm squared of that y vector. This part is not terribly interesting, so I can just focus on this part of it. So maximize the norm squared of y subject to some constraint on x. Obviously, I can keep making the received signal stronger and stronger and stronger by just sending a stronger and stronger signal. But obviously, I don't want to do that. I want to say, for a given amount of transmitted power that I have, I want to get the maximum amount of it to the target. So that's why we have this constraint here. And we can just pick c equal to 1. There's no reason, for the same reason that we just saw earlier, that without loss of generality, WLOG, we can pick c equal to 1. And so here's our norm squared for y. It's y transpose times y. But we know the structure for y looks like that. We know the properties for transpose shifts things around. And guess what we have? We have maximizing a quadratic form. And guess what we have? H transpose H. Columns of H are linearly independent. This thing is positive definite. So we've got this problem that we have already figured out how to solve mathematically. And this thing shows up all over the place. This is not just for this, maximizing the acoustic transmitted power. It shows up all over, all over. Let's continue. So I've already given this away. Is H transpose H really positive definite like we assumed? Well, by definition, positive semi-definite would look like this. We know that since this is the norm squared of something, that it must be greater than or equal to 0. So that tends to tell us that it's at least positive semi-definite. But we can also, as we just said earlier, you look at the structure of that H, and it's highly unlikely that you're going to get an H for which this thing is not positive definite. But the reality is since we're looking for the largest eigenvalue, whether it's positive, semi-definite, or definite, it's not going to matter. That will not change the fact that whether we can find the largest eigenvalue this way or not. Remember, semi-definite just allows the smallest eigenvalue to be 0. So we're in good shape here. So if we know the H matrix, we can solve this. So and this is somewhat of the contrived part of this. So imagine that we're setting up some sort of scenario. We're picking the position of our transmitter. We're picking the position of our receiver. And once we've picked them, they're fixed. And the reflectors aren't going to change either. And I can't really think of a good, real-world scenario where that might happen. But it could happen. You might want to set up some acoustical scenario or some architectural scenario where you could always get the maximum amount of sound from one place to another. Maybe you want to do that. I don't know. But this is the contrived part of this to some degree. But once we have everything physically set up, we could just send a signal that basically boils down to sending a very narrow pulse, so that in our signal model we just grab one number where the pulse is non-zero and everything else is 0. So our pulse has to be narrow enough, narrower than our capital T spacing of our samples to get this to mathematically work. But again, this is all approximation, and it's close enough to get us to where we need to be. If I send that signal X through, what do I receive at the other end? Basically, I've extracted one column of H from that. And if I do that by sending out lots of these little pulses, I can actually form the H matrix. And then, once I have the H matrix, I can form H transpose H, and I can find the eigenvector of that corresponds to the largest eigenvalue. And that eigenvector will be the signal that I should transmit. So here's some MATLAB code and an example of that. So I'm creating a little h vector. That would be one of my columns. And then this is a special command. You'll learn about that if you go on to further signal processing classes. So I'm not going to go into the details of that, but it's just a clever little use of a MATLAB command for something else that actually allows me to create my H matrix. So just trust me, it gives the correct H structure. I tried it, I tested it, I know what I'm doing. I'm an expert at this. Been doing it for a while. Now I'm going to form my R matrix, and now I'm going to find the eigenvalues and eigenvectors of that. I'm going to extract the eigenvalues into a vector. I'm going to find the largest eigenvalue using the max command. Remember, this will extract the value of that maximum eigenvalue, and this will tell me where it is. So I then extract out of my vector, or out of my matrix V, which has all the eigenvectors in it, I'm going to extract the column that corresponds to the largest one of it. And then I'm going to just create a signal sample index n so I can plot it against that. And I'm going to look at what this signal looks like. And then I'm going to label it, because if I don't label my plots, they're just art. And I'm going to normalize this just for convenience to use in the sound command, which will allow me to hear what this thing sounds like. Now, I don't have MATLAB fired up here, but you can run this code and hear what this thing sounds like. So you can listen to it. It'll just sound like a tone. Boop. And then we can plot it and we can look at it. So if we zoom in, this just kind of a lot of plotting artifacts. It looks like it's solid here. What am I plotting? Well, when you see a plot that looks like that, zoom in on it to see what it looks like, because all you're doing is coloring with a crayon, very quickly up and down, very close together. But if you zoom in on it, you see something that looks like this. And so you can see, I can't draw, you can see that this kind of looks sinusoidal in a sense. So this is a sinusoid, and this is how its amplitude changes over time. So when you listen to this, you'll hear it grow in volume up to a peak and then go back down. It does it pretty quickly. But that's the end here. This is hopefully showing you that these kinds of things really do show up all over the place. Well, we didn't establish the all over the place, but we showed that you start off with some seemingly physical problem. You apply some mathematical modeling to it. You do a little bit of approximating functions by samples that you put into vectors. And before you know it, you end up with a linear algebra problem. And you end up with, in this case, an eigenvalue problem, because we're trying to maximize a quadratic form. It shows up all over the place. And hopefully this gives you a good idea of why that is, and makes you go, hey, all this stuff I'm learning does seem actually kind of worthwhile. All right, I'll see you in the next set of notes.